Hello, welcome to Special Relativity Part 1. This is the third part of our roadmap. Show how the experience of the presented reality leads us to Einstein's theory of relativity. But this sentence may give us the wrong impression, so let's clarify. When describing reality, I already stated all the rules. Note that I described a certain reality. So I could have said information travels along a straight line that is perpendicular to a world line, or that the natural trajectory of a world line is a circle. But I described the reality that special relativity implies. And this means that this reality does not explain special relativity, rather it is special relativity. So it should be of no surprise to us that we can get special relativity out of the reality that is built according to it. This means the belief of special relativity describing the correct reality, and I remind you this is a reality without gravity for the moment. So this belief comes from it agreeing with our observations. Other descriptions of reality do not agree with some observations, while special relativity agrees with these observations too. So special relativity is a better guess of what the reality is. That's where we get the validity for special relativity. It agrees better with our observations. Now, if the described reality is special relativity, then aren't we done? Well, what we call special relativity is reality, but when viewed from our actual world experience. So we want to translate the rules to this perspective. We want to answer some questions like, how do the rules look from an inside perspective? For example, how does a straight world line translate to actual world experience? Another interesting question is, how were the rules discovered from an inside perspective? So we are restricted to our view of reality, and this includes the discovery of rules. So to answer this question, we need to find out what is the methodology behind rules. And we will start with that. So to find a rule, we observe and then look for a pattern in the observation. For example, a rule could be, it rains when I see clouds. But notice that this rule is specific. It only pertains to me and a limited range of situations. It is also not precise. It is not quantified and uses words, which many times are not exact. Science tries to find rules that are general. So one rule explains a broad range of situations in all the places and times where they happen. And this means observations need to be done for different situations at any time and everywhere. We also want the rules to be precise, which means we should use a mathematical language. And that means observations need to be quantified. And by the way, this also allows us our previous goal, because once we quantify our observations, we can compare them between different situations and different places and different times. Now our perspective is of experience, going through our world line point by point. This means we do not see the rules, rather we experience them. And this tells us a thing has a measure of ongoing, it has a time frame, and it has a measure of change, which is a placement. So we can compare if the place is the same or not in relation to us. And in this way, we detect change. So a thing's measure is its measure. If we want to move towards the scientific rule, we want to change this individual measure by making it precise, which means we need to have numbers for observations, and that means we need to calibrate experience. And as we said, calibrating can also allow us to look at different situations that can be compared using this same background. And calibration could also allow us to make observations anytime and everywhere. Again, this is from the same reason of a set background that once we have, we can use to compare things. Accordingly, to calibrate something, we want a procedure that will give us the same outcome, so the same scale, every time and place we perform it. Everything needs to use this same procedure. In this way, we can use observations by different things and still compare them. This allows us to have observations anywhere and anytime. But we need to be careful, and the procedure should be performed from the same type of things. So we want to make sure that the difference between the things does not affect the outcome of the procedure. And to satisfy this requirement, we will be using straight world lines. The idea is that in the model, straight world lines are in a natural form, which means this is the only rule acting on the world line. And this rule stands on its own. It does not depend on other world lines. So a world line wants to stay in a straight line without it caring about any other world line. And this means observations done from these straight world lines can be compared to find out all other rules. So all other world lines are a result of a mix of a few rules, which means observations from them cannot be used for comparison without first figuring out their own world line and taking into account the effects of its trajectory on the observations. And as a reminder, we as part of reality only know about relationships between world lines. Okay, so let's move on to calibrating. Now, experience is ongoing change, which means we need to calibrate ongoing, which will give us a time frame. And we need to calibrate change, which will give us a space frame. Let's start with time. To calibrate time, we look for information that we can identify uniquely and that has a constant cycle, a repeating behavior. And when we have something like this, we call it a clock. So here we have Alice, and here we have a world line that has a repeating cycle. Remember that Alice also has its own repeating cycle. And the purpose of this world line, which we call the clock, is to quantify this cycle. Now this cycle gives Alice a measure of change. And these changes are the changes that happen along Alice's world line, which means that Alice's time is parallel to its world line. And this means that we have to find a clock that has a repeating cycle in the direction of Alice's time. Once we have this clock, then we can identify the repeating cycle on our world line. And I'll remind you, the field that is created at this green point over here is affected by the distance along this information track. So if we look at this point over here, the information track is longer and the field at this point will be weaker. And the same for the point on the other side. this point over here will be with the weaker field. So we can identify this green point uniquely. And for example, we can decide that the interval between this green point and the next green point is 1 second, or 1 minute, or 1 hour, depending what we decide. So this is the way that we calibrate time. If we look to this situation with Bob's world line, the changes that Bob feels are along its world line, and therefore its time is parallel to its world line, and accordingly the clock has to have a repeating cycle in this direction of Bob's time. Moving on to space, to calibrate space, we look for information that we can again identify uniquely and that is constant. So the relation to our world line is constant, and this means the distance between us is constant between the two world lines. Again, if we look to Alice, we have a certain type of world line, and its relation to Alice is constant. So the distance between them is always the same. And this means that the information that we get from this world line is always the same. At any point, I just depicted some of them. And this specific information that we get is indicative of a certain distance from our world line. And again, if we look to Bob's world line, we have the same type of a world line, but it has to have its relationships constant with Bob's world line. However, we are not done with calibrating space. Distance is between 2 points, or between 2 elementary particles. So between which 2 points on the world lines is the distance. We need to define simultaneity. And simultaneity is when do 2 points happen at the same time. Once we have that, those are the 2 points with the calibrated distance between them. Now, the first idea that comes to mind is to say that when we get the information and when it was sent is the same time. So from our outside perspective, the length we are calibrating is the length of the information track between these 2 points. The idea is that the point where we receive information and the point where this information originated from happen at the same time. So these 2 points happen in the same time, and these 2 points happen at the same time. Now, if we look at all these points, we can establish Bob's space at a certain time. So at this time, let's call it time 1. This will be Bob's space, the 2 blue lines. In this idea, the speed of information is infinite. Now, with the structure of reality being as described, this leads to a contradiction. If we send information to a thing and it bounces back to us, then if the speed of information is infinite, we should get it back immediately. So nothing can change between sending and receiving the information. But as we can see in our model, these 2 points are different points on a world line, which means there is a change between them. So because we said that information tracks exist, so information has to travel along existing tracks, then if we send information from Bob at this point, it reaches the red point over here. And according to our first idea, these 2 points happen at the same time. And once this information bounces back to Bob, again, these 2 points happen at the same time, which should mean that these 2 green points need to be the same point. But because the structure of reality as we presented includes these existing information tracks, this cannot happen. Time is a measure of change happening, which means the cause for change cannot happen at 0 time. And as information is the cause for change, information cannot happen at 0 time, and we get to the conclusion that information has a finite speed. So our first simple idea cannot work. Now the second idea we can think about is that if we find the speed of information, then we can figure out when the information was sent, and the calibrated length is between this point and the point where the information left the calibrating world line. So if we know the speed of information, we can calculate when the information that we receive at this point on Bob left the calibrating world line over here. And let's say we figure it out and say this is the time that it left according to the speed of information. This means that this point and the point where the information left from happen at the same time. And if we look at all these points, we can define Bob's space at time 1, which will be this time over here on its world line. But this idea runs into a circular argument. To find out the speed of something, we need to have a calibration for length. And to calibrate length, we need the speed of information. So we are stuck. So the third idea is that we need to find a procedure that everybody can do in the same manner. And this procedure needs to give us a point on our world line that, together with the point where the calibrating information left from, will define simultaneity. This is our goal. Now the idea is that if we send information from a point on our world line to a thing, and it bounces back from this thing, then we receive it back at a point on our world line again. And we say, so we assume this, that the time it takes information to go one way is the same as going the other way. So anytime we send information to something and it bounces back to us, we say that the information takes the same time to get to this thing as it takes to get back from this thing to us. And once we say this, we can use the midpoint between sending and receiving the information as the point on our world line that is simultaneous to the point where the information hits the other thing. And the distance that we calibrate is between these 2 points. And if we find all the points that adhere to this procedure and give us the same midpoint, they are all together defined as space. Okay, here we have Alice, and this is the procedure. We send information from a point on Alice. It hits our calibrating tool at this point over here, the red point over here, bounces back and hits Alice back at this point over here, the top green point. Now, if the information takes the same time getting to the calibrating tool and coming back, then the midpoint between these 2 sending and receiving points on Alice, so this red point over here, which is in the middle, is the point that happens at the same time as the point on the calibrating tool where the information bounces off. So these two red points are at the same time. Now if we look at all the points where this type of procedure gives us the same middle point on Alice, then we can find Alice's space at time 1. Time 1 is all the points that happen at the same time as this red point on Alice's world line. And if we use this same procedure and the midpoint is this point on Alice's world line, then this will be Alice's space at this time. Let's call it time 2. And if we look to Bob's world line, this is our procedure. We send information from this point on Bob to the calibrating tool, and it bounces it back to Bob, which receives it back at this green point over here. Again, we say that the information takes the same time to go in one way as the other, which means the midpoint between these sending and receiving green points is the point on our world line that happened at the same time as the information hitting our calibrating tool. So these two red points over here happened at the same time, and accordingly this is Bob's space at time 1. These are all the points that once we use our procedure will give us the same middle point of this red point on Bob. And if we use a procedure that gives us a middle point over here, then this point on Bob's world line and this point on the calibrating tool happen at the same time, and accordingly this will be Bob's space at time 2, which is at this point on its world line. Now note that in actual reality we have 2 more dimensions. So space is defined in 2 more directions. We need to have this procedure happen in 2 more directions, and this means space is 3-dimensional. Another thing to notice is that at our point in space we do not have information about other points of space. Other points of space happen at the same time as our point. However, information takes time to get to us, and this means that no one sees its space. From our perspective, space is an abstract. We figure out where things will be in space according to the information we have on them. And that information is from our past. Okay, let's look at 2 world lines together, Bob and Alice. And both Alice and Bob did the same procedure using the same things. So same clock type and same stick type. And they used these same things to calibrate time and space, and accordingly they got their coordinate system. Bob has the green coordinate system and Alice has the brown coordinate system. And now that we look at 2 world lines together, we want to understand what is the relationship between the 2 coordinate systems. The relationship is according to how the same type of clock and the same type of stick transform from Bob's world line and Bob's space to Alice's world line and Alice's space. And just to note the depiction is not correct. I just chose a random relationship so we can study it. So let's try to guess this relationship. But before that, let's see how to work with the coordinate system itself. Okay, so we have this point, which is both on Bob's and Alice's world lines, which means they can both agree about this point. And therefore, let's use it as the 0, 0 point of the coordinate system. So this is times 0 for Bob and times 0 for Alice. And this is space 0 for Bob and space 0 for Alice. Now we use our procedure and we find Alice's space at this point, which is this blue line. So this will be Alice's space at time 0. And we use the procedure from Bob's word line and we get Bob's space at this point, which is time 0. So this blue line is Bob's space at time 0. Now let's look at this star over here and try to figure out where it happens compared to our starting point and at what time it happens compared to this starting point. And let's do it first for Bob. So what we want to do is find Bob's space at the time that star happened. So this is a parallel line to Bob's space times 0, but it goes through our star. And this means that we need to count how many time coordinates are between these 2 points on Bob. So here we have point 0, here we have point 1, the green line crossing Bob's word line, and here we have point 2, the second green line crossing Bob's word line, and this is point 3, the third green line crossing Bob's word line. And the same for space. We need to count the green lines of space. So this is the first green line, and this is the second green line, and it goes through the star, which means that the star is point 3, 2. It happens 3 seconds after our 0 point and 2 units of distance from our world line. And this is for Bob. Now let's do the same procedure for Alice. So first we want to find Alice's space at time star. So this is the parallel line to Alice's space at time 0, but it goes through the star. And again, we need to find the distance between these 2 points according to Alice's coordinates to figure out the time difference. So here we have the first brown line going through Alice's world line. So this is 1. And this is the second line that goes through Alice's world line. So this point is about 1.75 according to Alice's coordinates from the 0 point over here. And distance-wise, we go and find that the star is 1 unit of coordinates, this brown line over here, away from the 0 line, the world line of Alice itself. Accordingly, this will be 1.75, 1 in Alice's coordinate system. Okay, now let's try to guess the relationship between these 2 coordinate systems. And because we use the same procedure and the same things, my first guess is that the units need to be the same. So when Alice looks at Bob's 1 second, it will be her second too, and vice versa. However, when we look at the model from our outside perspective, it seems this guess is problematic. Or, in other words, it cannot happen in the described reality. So the first idea that we consider is that Alice sees Bob's time as she sees her own, and the same for Bob. Bob sees Alice's time the same way he sees his own time. So if we look at this star over here, and Bob sees this star happening 3 seconds after the 0 time of his, which is the same 0 time as Alice, then Alice should see this star also happening 3 seconds after her 0 time, which means that this number over here needs to be 3, and we got the spacing between the coordinate lines the wrong way. Should be 3 brown coordinate lines between this point and this point. So let's say we got it right, and this means that this point will be 3, 1, and this point will be 3, 2, which means that Bob sees this star happening 3 seconds after its 0 time, and Alice sees this same star also happening 3 seconds after its 0 time. So they see the star in the same way. However, Alice sees all these points along this blue line, as points that happen 3 seconds after its 0 time, while Bob sees all these points along this blue line as happening at 3 seconds after its 0 time. So any other point that is not this star, Bob and Alice will not agree about. If we look at this point over here, from Bob's point of view, this point happened 3 seconds after its 0 time, while for Alice, this point happens less than 3 seconds from its 0 time. Which means that if we want Bob and Alice to see their time the same way they see the other world line time, we need the lines of simultaneity to be parallel. And this happens only if the world lines are parallel. In that case, we have the same coordinate system. But any time that we have an angle between the world lines, then the lines of simultaneity are not the same lines, and therefore we cannot see the other world's line time the same way as we see our own time. With the way we describe reality and the assumption that it takes information to travel to a point and travel from this point back the same amount of time, we get coordinate systems that cannot work with this first idea we thought about. So we still need to find out what the relationship between these two coordinate systems is. And basically, this relationship is special relativity. And we will see how this is done in the next video.